All right, welcome back to Loving the Physics with Mr. Goldthorpe. We're going to take on Lesson 5, which is on reflection and interference. And for reflection, I'm just going to show you guys some videos on this first. Let's start with something called fixed end reflection. And here you actually have kind of a string, a spring, whatever it might be. And here's what was called a positive pulse coming in towards it. And notice that it's fixed against a wall on the right-hand side. Now watch what happens to this pulse as it comes and hits the wall. Waiting. Okay, that's cool. So when this thing comes in, you'll notice that what happens is it goes back the other way. It reflects, but it reflects upside down. It does what we call inversion. Reason? When this pulse is actually coming in towards the wall, it tries to lift up on the wall, exerts an upward force on the wall, and the wall exerts an equal but opposite force down on that string, and therefore flips it upside down. So for fixed end reflection, it flips upside down. Good, that's the first one. Now we also have something called free end reflection. And this time, instead of a wall, we have kind of a ring on a frictionless rod, so it moves freely. So we call it free end reflection. Again, if we bring a positive pulse in, the question is, what's going to happen when it's not even hitting a wall? Well, let's find out. Waiting. There we go. Okay, cool. Notice it still reflects. But it reflects back upright because it doesn't experience that equal but opposite downward force. Instead, it reflects back due to elasticity. And there we go. So it kind of, as it comes into the ring, it stretches it out and then it snaps back and gives you that reflected pulse. But there's no inverting. Good. That's free end. So we can see those things in our notes. This one kind of summarizes the two. So understand again that when you have, in this case, fixed end reflection, you'll see that it comes back inverted. As you can see right there, it flips because it experiences that equal but opposite downward force from the wall. But when you have a free end situation, it will still reflect, but it comes back upright because it does not experience that force downward from the wall. That's pretty much all you need to know about the two kinds of reflection. Now, let's move on from medium to medium. And I think what I'll do for this one is let me show you the video for this when we're going from one medium to another. So, back to the drive. And this one, we're actually going to go from, I believe, thinner to thicker. That's what we're doing. So, let's take a look at it. So here we have a positive pulse that's going from a thinner or faster string to a thicker, slower string. And I just want you to notice what happens when this pulse comes in. And we'll see how long it takes before I have to wait for this. Wait for it. Waiting. I think we're ready. Good. Okay, cool. And you'll notice that the wave actually splits up into two waves. One wave continues into the new medium, and the other wave reflects backwards. So we get partial reflection and partial what we call transmission into the new medium. But the energy splits up into two parts. And your job is to be able to predict the nature of both parts. And let's talk about how we do that. So let's go to our notes and try this ourselves. So this is what we have in the notes here, is a situation where we're going from, let's say, well, we call it fast to slow. This could also be going from thin to thick, if you wish, tight to loose. There's lots of different descriptions for this, but essentially going from fast to slow. And our job is to figure out the nature of the two different kinds of waves that are produced. So we're going to start on the left-hand side with reflected. And I want you to see if you guys can answer each of these questions. Do you remember what property of a wave never changes once it leaves the source? Answer, frequency. So for the reflected pulse, we know the frequency is going to stay the same because frequency never changes once it leaves the source. Good. Now when it reflects, can you see it's going to be going back in the same medium? The medium stays the same. It's the same as the original pulse. Tell me, if the medium stays the same, what else must stay the same? Answer, speed. So here, the speed stays the same because the medium stays the same. Now, what if we wanted to find out about the wavelength? Well, if you want to find out about lambda, think flamda. So, if we take a look at V is equal to F lambda, it should make sense that if F and V stay the same, then lambda has to stay the same as well, by requirement. So all three of those are going to stay the same. Good. Next, let's talk about amplitude. Now amplitude, if you remember, relates kind of to the energy of a wave. That's part of its definition, partly to energy, especially in the same medium. And do you remember how this is going to split into two different pulses? So the energy splits up, so the reflected pulse will have less energy. So the amplitude has to decrease. Last but not least, I guess our big question will be, does it go back inverted or upright? So we're wondering, would this better relate to fixed end reflection or free end reflection? That's a tough question, actually. But the idea of it is, if you take a look at where these things actually meet, you'll see that it's coming into a much denser, thicker medium. Now, a heavy, dense medium is kind of more like a wall. A wall is very heavy, very dense, much more massive than the actual spring or string. So because you're going into thick, heavy material, that is more like a wall. So that will be more like a fixed end reflection. Do you remember, if it's a fixed end, does it invert or not? And the answer is, it inverts. So it comes out inverted. So if I was going to draw this, I don't know what color I want to use for drawing it, then what we can do is this. We can kind of draw some dotted lines here for some reference, and we want to bring our wave up to that point, and we know that it's going to have a smaller amplitude and be inverted, but have the same wavelength. So it's going to look like this. Oh, no, that's not what I wanted. If you take too long, that's what takes place here. Like that. Can you see it's a smaller amplitude, but the same wavelength? And it's going back the other way at the same speed. So we want to make that arrow be the same as the original arrow. So that's how we draw the reflected pulse. So far, so good. Now, let's take on the transmitted. So we know already that the frequency has to stay the same because that never changes once it leaves the source. Now speed. When it goes into a thick, loose medium, it turns out this is going to cause the speed to decrease. It goes to a slower medium. Now again, if we take a look at V is equal to F lambda, we want to know what happens to lambda. Can you see that F stays constant, so lambda has a direct relationship with speed? Well, that means if the speed decreases, lambda has to decrease too, because they have a direct relationship. Good. Now what about amplitude? Well, there's a couple of reasons for amplitude that I can tell you. I know that amplitude is definitely going to decrease, but there's two reasons why. One, because the energy splits up, so there's less energy, but actually more important than that is you can see when this pulse comes in, it's trying to lift up a very heavy medium, that thick, loose medium. And this is kind of like you trying to lift up a really heavy rope. Have you ever tried doing that? When you try to lift a very heavy rope, it's hard to lift it very high. So because when you try to lift up a massive object, the amplitude has to go down. You just will not be able to lift it very high. So there's two reasons here. Less energy, and also because you're lifting a very massive rope. So the amplitude is going to decrease. Next, will it be upright or inverted? And again, the idea is, if we look at the new medium, that pulse that's coming in it is a crest that's coming in, and it's going to try to lift up anything that's in front of it. So that means it's going to stay upright. And if you want to make a general conclusion, the transmitted will always have the same orientation as the incident. So if it's upright coming in, it'll be upright going into the new medium. So let's draw that. We want to draw this new medium with a small wavelength and a small amplitude. So it kind of looks like this. Let's try to make it thicker. Make it pretty extreme too. So there's our kind of our thick, loose rope, if you wish, and it's going to be moving at a slower speed. All right, and that summarizes the properties. This is a very important example for Physics 20. Look at all the different review that we actually have here. So what I'll do is I'm going to give you a chance to do one of these on your own in this, and when we do our next part of our lesson. So I'll see you then.